Hi everyone, thank you for attending this presentation. So this presentation is about presenting a boot time optimization project. So in the boot time optimization, usually what we say it's okay, it's platform specific. When you do the change for this platform, they are lost for the other platform because they are not applicable. That is true, but only partly, because we can find always the same problems coming from the different platforms. So the problem we want to solve here is some system must be ready very quickly, as soon as possible when you power on the system. One example is the car. When you enter the car and power on the car and you set the rear gear, you want the camera coming immediately, not waiting 15 seconds to see what's happening behind the car. Also, when you are sticking to upstream code, when you can have contribution from your outside where you don't have control on these changes, and these changes can introduce latencies on your code, and you have to find the fixes for this and changes introduced by the outside world. And another aspect is when you do a boot time optimization on your platform, you can lose the knowledge across the time because you have turnover with the team, the expertise can be lost, and the new team has to investigate again what they can do to optimize the boot time. And finally, one of the problems we have is we have few interaction related to the boot time between the firmware and the kernel user space when we have all the boot process. And so what's happening is usually we can have duplicate work. The firmware is doing things and the kernel is doing the same things. And we don't have a way, so the kernel does not trust the firmware to do the right thing. Maybe it's right, but at the end, it is doing the same thing, the firmware. So it's a duplicate work, and obviously that introduces more latencies. So the goal of the project is try to optimize the boot time, any firmware, kernel, user space, track down the boot time when there are changes all the time. When we do changes where there is a boot time improvement, then we want to document this information somewhere so we can access this information for if someone is interested in doing the same optimization later. And we want also long-term support for these boot time optimizations. So the proposal of the project is to create, first we have to choose a reference platform for boot time optimization. So that this does not mean, it means it must be something representative. So we can, there is a good support and we can do the improvement on this platform and see the improvement time by time. The idea also is to use code linear for automated non-regression testing for the boot time, and maybe, so that's just a proposal, maybe use AI so we can figure out where it's coming from the regression. Use the knowledge base we have with code linear because we have a wiki support also. And finally, all the changes we are doing to do the boot time optimization, then we upstream these changes, so we have with this the long-term support. So the boot time priority is something not necessarily high when, depending on the kind of material you are using. For you have a computer, for example, or a laptop, you don't care the amount of time. Obviously, if it's taking minutes and minutes to boot up, then it is becoming really critical to have an optimization of the boot time. But otherwise, if it's in an acceptable amount of time, then you don't care. You have the laptop, you just close the laptop and open the laptop, go to suspend and resume, and it's okay. You don't pay the cost of the powering up all the time, the boot time. The server are always up, so it's very rare when you pour down a server. And the IoT is going, yeah, they boot fastly, but they are getting more and more complex. And with this complexity comes more initializations and also more latencies introduced at the boot time. So in this case, you have to take into account the boot time optimization. Then you have set-top boxes, mobile phone, and multimedia. So it's always a moving target. You have to optimize. So it's okay until you are in an amount of time, but as soon as you have more complexity on your system, then you have to take into account this boot time optimization to prevent to have the system taking too much time to boot. And then you have always very high boot time. The boot time priority is very high for all these, let's say, in a life safety constraint context. You need to boot up, for example, healthcare devices. You don't want to wait for 1 hour to have this device to power on if you want to take care of someone. So automotive is the same, and avionics, obviously, you have to have the system to boot up very quickly. So because it's the boot time is target, it's continuously changing because you have changes going from the outside, and your changes can introduce boot time regression. You have the first step is you have the platform enablement. Then you do after that all the boot time optimization. And on the other side, when your platform is enabled, you have to do a continuous integration to make sure you don't have a boot time regression. And at the end, you end up by profiling the boot time all the time. What's happening with the boot time optimization is it's a complex process because it touches different level on the stack, on the hardware, and you need to have people with a high level of expertise to understand what's happening with the firmware, what's happening with the kernel, what is happening with your user space, how they interact, what is the impact of one to another, and so on. If you want to optimize the code and upstream the code, you might have an impact, significant impact in the open source code, and you need to have people who are actors and having credit in the community to do all these changes, so you don't have this optimization coming, being upstream after months and months. You can have more quickly these optimizations. And finally, you need to capitalize all the knowledge. So in the boot time, you can find these 3 components, where the firmware, usually we have driver delays introduced. So drivers sometimes are not very well documented. So when you are trying to make them working, then it results that you introduce delays for initializations. And all these delays, we find that in the different drivers are adding summing. And then that introduces a lot of latencies when you boot up the system. Also, you can have a bad performance index. So you initialize the performance mechanism, CPU freak, let's say, for example, too late. So that means your system is not booting at the highest performance index, but on the middle or the lowest one, and it is slower. So that's one of the reasons where you can have your system is not booting very fast because there is this performance index is too low. And you can have file system access, which is not correctly done. For example, one example is when you try to run, you read file and you read small amount small amount of data instead of big chunk of data. That's one example. Or you don't use the mechanism provided to parallelize the read and so on. The kernel has a bit more of reason of having a boot time regression, a boot time optimization area. So yeah, we have serialization. That's one of the reasons. So if you initialize things, you wait for the first thing to initialize the second thing, and if there are no dependency between two, you can do that in parallel. But we can find in some parts in the kernel things are done in serially. So it is introducing bottlenecks in this initialization path. You can have load balancing. It is not correct. The compression is one of the example. Compression of the image, and so on. So that's all the areas of improvement you have in the boot time. And in the operating system, so that's another set of example. Serialization also of the starting of services. You can have the logs. You can have a lot of logs, and the logs are very slow. That slow down the system a lot. And you can have also this performance index thing. So you can have the system is starting in too low performance index, and all the user space initialization it's not going in the right performance index. So you can have all the changes, and you see that you finally succeed to have your target for the boot time. And between your changes and this goal, you can have months and years, and hundreds of thousand changes come from one version to another version. And when you realize you switch the version, then you realize the boot time optimization is just broken, because all the changes introduce latencies or something in the boot time process, and you are unable to find it out which one it is. So it's a lot of work to investigate and try to re-enable all this boot time optimization. But if we do smaller amount of changes, and every time we have a change, can be from outside or from inside. So when I say outside, could be coming from outside contributor, or from inside from the company doing the changes. Then when there are changes, automatically you do a check with the boot time and make sure that you are still in the target you decided to have. If you have a regression spotted, as there is a small amount of changes, then you can spot immediately the culprit and do the fix very quickly. So today in the boot time, what we have some existing tools. So from user space, from the tools point of view, we have the user space. We have bootchart 2, systemd analyze, and bootchart for Android. And the one which we are interested in is this one, because actually it supports most of the timing information we have available from the firmware, from a CPI, and from UEFI. UEFI for U-boot, we have UEFI variable giving us the amount of time we have booted and loaded the image, loaded the kernel, booted the firmware. All this information are in UEFI variable, and they are used by systemd analyzed. And we have more or less the same amount of information in a CPI, and systemd analyze and present us in the same way the information. So basically, we don't have to care about how the kernel is presenting us the information, because systemd in user space is giving us this information. But some firmware do not have this UEFI implementation to exporting this variable, so we have to add that. I think there were already some proposals to do that, so that's the case of U-boot. At the kernel level, we have some, let's say, some way to have. So there is a new option here, the boot time tracing, so we can have timings for the different subsystems when we boot. But let's say that it is not interested from the project yet. That is interesting when you spot a regression and you want to investigate where is the bottleneck in the boot time. The project today is, we are starting here. We are in this moment where we are trying to define the project is very broad. It's very big because it touches the firmware, it touches the user space, the kernel, and we don't want to take everything into account. So we have to define the scope of the project first to do the first steps. So the idea is to this definition, do the continuous integration, and then do all the engineering stuff around firmware, kernel, and operating system. So the first step is we want to stay focused on kernel and some part of the firmware. First of all is to find a way to measure the boot time and pass this information from the kernel from the firmware to the kernel, and from the kernel to the user space, so we can read that from systemd. And we want to have this continuous boot time measurement regression analysis. So the idea is to use Linaro, Lava, SQL, database, well, what the infrastructure we have available here in Linaro. So for the boot time, for the potential areas of improvement we find, so I would say that the most important one is this one. So the idea is let know the kernel what devices we already initialized from the firmware. So we don't know yet how to do that. We are under discussion, but we think that it is the feature that will improve the most the boot time regarding the kernel, firmware and kernel. The other things are more related to the information. So the first one is boot time chain timing. So if we have different firmware loaded, we don't know which one is taking time. We have just the information about between the system boot up and the kernel started. We have this amount of time, but we don't know which in the process in the boot chain which one took the most the longer time. And the information, boot information, that's what I said before. So we want to present standardized timing information to collect from user space, the user space tools. From the kernel side, so we have a set of things. So for example, compression use LZ4 and reduce unit RAMFS. That's a common way to optimize the boot time. So it's not really interesting in terms of generic framework. But we have things like, for example, parallelization. When we start Amazon, we restart Amazon, they are done in serial, and we can have maybe 30, 40 terminal zones on the system, and that can take a non-negligible amount of time to just initialize the terminal zone. So the kernel is stuck in there to initialize that. So that's an area of improvement, because there is no dependency between the terminal zone. They can be started in parallel. Another request we had is memory initialization. So when we have system with a big amount of memory, it takes a long time to set up the memory. So that's things we are discussing. Yeah, so there are different file system. Investigative BFQ is enabled. After all the CPUs are up, so we are also talking about a parallelization of the request. From user space, it's the same. We have file system access, so make sure that we are trying to read. We can use read ahead if it's used correctly. Remove all the logs. So that's more generic. But for example, there is an interesting aspect, is parallelization. When we read the module, can we, with mod probe, read and load the module in parallel? That's the question. Can we start the services in parallel? So the plan is, first, we have this CI loop. We implement the missing firmware for UEFI API in U-boot. We automatically detect the branches change when you are doing development. You have outside branches, upstream branches, and your changes. When you detect one change, when the system is detecting one change, automatically will integrate all the branches into an integration branch and compile and boot. All the boot time measurements are stored in the database, so we get all the history of the boot time. What we don't want to dig into, we want all this data to be presented in a simple way. We don't want to be digging in the data and find out the information. We want to see a nice graphic, a time series, and we can see, poof, up here we have a peak of boot time, so let's investigate that. And when we detect a boot time regression, we want to send an email. But the boot time regression is not only about detecting the boot time duration is higher, because if you change your strategy, your policy, of your platform, saying, okay, I want to boot, but I want to take less power, less energy when I boot up, then automatically that has an impact on the performance, and that will increase the boot time. But it's a choice. It's not a regression, it's a choice of the policy. So what is interesting with that is to tie that with the temperature, with the power consumption, and the performance. So the boot time, you can then really analyze the boot time information when you have the other information. So you can say there is a problem. If you have a boot time increase, but you have the thermal temperature increasing, that gives you an indication about what's happening. Boot time, you can have performance, the same performance, temperature increase, but boot time increase. You can see that maybe there is a busy loop somewhere introducing this latency. And, well, that would be a nice to have, but if we can detect the changes, then we can have the beginning of the change and the end of the changes, and we can logically identify the commit ID. But it's a bit complex to achieve. That would be nice to have that, but not sure we will have time to do that. So I'll just skip that. So the second part is the engineering, all the engineering aspects. So we cannot work on the boot time optimization if we don't have first a framework where an infrastructure when we can track down all the boot time. We need to make sure that we can work in an engineering aspect and have an integration and see how our changes are impacted the boot time. Without a proper infrastructure, this is not working very well. So that's the reason why this is split in two. We have this first part, which is really continuous integration and boot time regression detection, and then the second part, which is in engineering, so analyzing the systems what can be done in generic code, what is already existing in the upstream code, and then doing optimization with that. So obviously, one thing is to fix all the M delay we can find in the past. So are they really necessary? So demonstrating, so all the user space is, let's say, it's out of the scope of this engineering part because we have to reduce that in a kernel and firmware. There is this probe time optimization, which is very important from a point of view to prevent to do again and again the initialization of the devices, and memory outplug for big memory configuration. So when we are talking about big memory configuration, we can see a noticeable amount of time for memory initialization at 64 gigabytes of memory, and when we can have just up to 2 terabytes of memory, it takes minutes to set up. So today we have, at this point, we have a proof of concept, which is done with the Ben Copeland team. So we have a continuous integration, and we run and boot, get the boot time measurement, and that is rendering in a graphic. And after that, so there is ongoing discussion in this Connect to see how we can go forward with this project. So if you are interested in this project, just let us know. If you want to, that would be very interesting to have reference platform. If you have a platform and you want this platform to be part of this work of engineering and the continuous integration, boot time, optimization, and regression detection, then just propose your board. And if you have specific boot time optimization you would like to see implemented, or you would like to see upstream, just let us know and give us this requirement. Okay. Do you have questions?
Yeah, I have a couple questions. Have you looked, is most of the work that you've done on Android, or is it with like distros?
It's distros today.
Okay. Then my question then would be, with UDEV, have you looked at, or do you, I don't know, I'm not super familiar with UDEV, but does UDEV allow for parallel module loading? Like, does it do it asynchronously?
So that's something, it's not clear for me. I would say yes, but I'm not sure of that because there is this eProbe defer. That's something I cannot give a clear answer about that because it's still we are investigating, analyzing that, and I think it's possible to have, you can load the module and automatically gives you, it does that synchronously, but I'm not 100% sure of it.
Okay, because on Android we support loading modules in parallel, and we found that helps with some of the drivers that are not written correctly. So if you have delays in your initialization or in your probing, if you're loading those modules in parallel, then it kind of helps like hide away those delays. And then, like, for example, with the thermal zone initialization, if you can load your thermal module in parallel, then you can do that. You can add that parallelization without actually having to change the driver logic.
And did you modify ModProbe, or have you created your own?
Yeah, we've updated libmodprobe to support parallel module loading.
And did you try to upstream the code?
Since Android uses a init in libmodprobe, we have our own fork of that, so that's not upstream. But I'd be curious to see if, like UDev, if they added loading modules in parallel, if that would be helpful, and you'd see the similar improvements.
I think UDev can be set up to load modules when devices are added, but I don't know. It might still be serializing that part. I'll go through list of devices and adding the module one at a time. Maybe that's another place where I can parallelize. Instead of just parallelizing loading, as devices come up, load multiple modules for all the coming up devices at the same time. Like, because when you add a device, you can send a U event, UDev, like a user space event that UDev looks at. That's why we have the module something macro where we can define the compatible strings.
Yeah.
That's used to match up with the module names. So that's somewhere you can parallelize if it doesn't already.
Yeah.
And then one other thing on Android we noticed when we started moving to modules and moving them to load later, even when we were loading them in parallel, we noticed that there was a bottleneck in uEventD. So if you're looking at Android, that might be something to investigate.
Okay. uEventD. Okay.
Yeah, uEventD, when after cold boot, is all single threaded. So if you start loading a bunch of modules, it triggers uEventD to process all those events. And right now, after cold boot, that's all serial.
Okay, so you can parallelize the module loading, but at the end, you end up to have this bottleneck there when you send a notification.
Yeah, so to work around that, you can move your modules to load earlier before, like in first stage init. And then in first stage init, all U events are handled in parallel.
Okay.
I have a question, and I suspect there may not be an answer first, but I'm going to ask it anyway. I've worked a little bit with on boot time optimization for automotive, and it's really hard because there's an expectation around 2-second boot, and often if you allocate the firmware, say 1 second, that gives you 1 second to boot Linux, and yeah, that's hard. But one problem I find in particular is like really critical modules, like say storage. That's normally a critical one to get to rootfs quickly. Is if preferably it would be a module so you could ship generic kernels and not build things in directly. But when you build a storage driver in directly, the storage can start initializing before you even get to initRD user space. And you get a significant improvement. But we don't want to do that because it makes our kernel less generic. Because if you start building in every storage device driver you support, then you have a huge kernel. But that's a problem I've been thinking about, and I don't know how to solve. Are there ways to bring up initRD user space more quickly? And I know this is insane. Sometimes I think, should we think of ways of how to load kernel modules in kernel space somehow? But I know that doesn't exist. Have you encountered any of these problems, or?
No.
Okay. I tried.
Yeah. Okay. Last question.
Oh, sorry. I thought there was a way to trigger loading a module from the kernel. If you do it from a K thread, wouldn't you do it in a kernel thread context? Okay. Because I know like request module can trigger loading a module, and I think they might have even a kernel space helper, if I'm not mistaken.
Yeah, you need to define the user mode helper, mod probe. So you need to define the config that you can set for user mode helper to load, and set that as mod probe, but you need mod probe in your init ramfs. But I don't think there's a way upstream to tell which modules to load. In Android, we added support for that by defining the modules on the command line.
And this is the different module.
Excuse me. I think we are running out of time.
Okay, thanks.
And next day session. Thank you. If you want to discuss outside, it's okay. Thank you very much.